Okay, let's get started, please. So we are going to jump ahead into chapter 4, which is about continuity. Okay. And the reason that we're jumping ahead to chapter 4 is because chapter 3 is about sequences and series, but chapter 4 really makes use of the notion of compactness. Okay, so right now compactness is hopefully fresh in your minds, and let's use it to get some. Really, what chapter 4 is about is the interaction of continuity and compactness. Okay, the interaction of continuity and compactness. Okay. Okay. So. But to get to continuity, we have to introduce first a notion which all of you have seen before in one form or another, the notion of limit. Okay, so the notion of limit. Okay, so so if I say the limit of f of x is L as x approaches some point, okay, what does that mean? What does that mean to you? What does that mean to you? The limit of f of x is L as x approaches some point. Yes. Yeah, go ahead.
The point on the graph that L intends to reach at x equals p.
Yeah, so you've got this sort of intuitive idea, right, that there's this point p, and as your x's approach that thing, well, then the values are going to get close to L, right? Okay, so that's one way of thinking about it. Has anybody seen any other way of thinking about it? How many of you have seen epsilon delta definition? So some of you have seen that? Okay, that's all right. Okay, so the way you want to think, so there's another way of thinking about it, okay? And the way of thinking is like this. You say that the limit of L means that so let me say it like this. No matter how close someone wants you to be to L, right? No matter how close somebody wants you to be to L, there is a place where that is satisfied. Okay. There's a place where that is satisfied. Okay. So you want to think of this as sort of like a tolerance, right? A tolerance condition, right? No matter how tight the tolerance, right? No matter how tight the tolerance is required, there's a place where that tolerance is satisfied, right? Tolerance in a machining sense, right? You have to be within a certain precision. Okay. Okay. So let's think about this picture here, right? So I've got this picture, and this is what you think of when you think like the limit is L, right? But here the opposite way of thinking about it is like this. You think, okay, if somebody says I want you to stay between L plus 1 and L minus 1. I want you to stay within 1 of L. Can you find a place where that happens? Can you find a place where that happens? You say, yeah, sure. In this punctured neighborhood, everybody lies between L minus 1 and L plus 1, right? Everybody lies between L plus 1 and L minus 1 and L plus 1, right? So when we say place, what we actually mean is punctured neighborhood. Okay. Because it's punctured because, as you recall from your first encounter with continuity, you don't care with limit. You don't care what happens at that point, right? Okay, right. If somebody says, so let's go back to the tolerance idea, right? If somebody says, I'd like you to stay between plus half and minus a half, well, in this picture, I can find a radius in which that's satisfied. Right? And if somebody says, I'd like you to stay within a billionth, plus a billionth, and minus a billionth, well, I can find some place where that's satisfied with this picture, right? Okay, so no matter how close I'm required to be to L, there's a place where that's satisfying. Okay. So let me make it even more concrete. F of x is 2x, right? The limit of f of x as x approaches 0 is 0, right? Of course, right? So you've got this 2x here, right? You've got this function f of x equals 2x, and I'm saying that the limit of f of x is 0 as you approach 0. F of x is 0 as you approach 0, right? Okay. And I suppose I say, I'd like you to stay within 1 and negative 1. I'd like you to stay within 1 and negative 1. What punctured neighborhood gives me outputs between 1 and negative 1? Just tell me. Negative 1/2, positive 1/2, right? So if I take a tolerance of 1, right, a tolerance of 1, then I get a corresponding radius. I get a corresponding radius of 1/2, right? As long as I'm within 1/2 of 0, then my outputs are within 1 of 0, right? So tolerance and radius. Tolerance and radius. So tolerance of 1, a radius of 1/2, right? And if I say, I'd like you to stay within 1/2 of 0, well, what's the radius going to be? Somebody say, please.
Negative 1/4 and 1/4.
Right, so the radius is going to be 1/4, right? Because you need to stay between -4 and +4. Okay? Everybody okay? Everybody okay? Right, suppose I say, I give you a tolerance of epsilon. Epsilon is some tiny number. What's the radius going to be? Write it down. Take 5 seconds and write it down on a sheet of paper. What do you get, Max?
Epsilon over 2.
Epsilon over 2, right? Epsilon over 2, and you see that that's going to work, right? As long as you stay within epsilon over 2 of this guy, because the speed of this boat here is 2, right? Then it's not going to travel more than epsilon distance in epsilon over 2 time, right? Everybody okay? Okay. Okay. So what you see is that no matter what tolerance is given, there's a radius in which that tolerance is satisfied. Okay, so now let's give the real definition of limit. And now I'm afraid for you guys, we're going to use some vocabulary. Okay, so here's the definition. So you've got two metric spaces, x and y. Okay, so you've got two metric spaces, the metrics d of x, d sub x, and d sub y, metric spaces. And you've got some set in x, and you've got some point in the limit points of E. Okay. Okay. So, and you have some function going from E into the metric space Y. Okay. So you've got your metric spaces, you have x, y. You've got one metric space. You've got another metric space. X, y, you've got some function here, you've got some point, you've got some set x, you've got some limit point p in the limit, right? And you've got some function going from left to right. Okay? Okay. Okay. So, and there's this point q on the other side. So if there exists a point q in y such that, which has this weird property. Okay, so I'm gonna draw it out for you first. Okay, so everybody look up at the board for a second. Okay, so here's what we're gonna take as our definition of limit. It's gonna be this. Given any epsilon neighborhood of q, there's a delta neighborhood of p, so that all the points that are in p that are inside that punctured neighborhood are mapped inside of there. Are mapped by f inside of the epsilon neighborhood. Okay, this is exactly the same notion as this. Okay, right? You've got your map f, right, from here to here, right? And what we're saying is that given any epsilon neighborhood, right, 0 plus epsilon, given any epsilon neighborhood of 0, right, there was a neighborhood over here that all the points get mapped inside of it. Right? All the points get mapped inside of it. Right? All the points stay between negative epsilon and positive epsilon. Right? Okay, and it turned out for us that the radius that worked was epsilon over 2. Okay, that's not always the case. It would be some, but we were able to do it. Okay, so that's the definition, right? Given any tolerance around Q, if there is this point Q, so that given any tolerance around, right? So for any tolerance around Q, there exists a radius around P. With the property that everybody in E inside that punctured neighborhood gets mapped inside there, then we say that the limit exists. Yeah, all right.
Why was it necessary for P to be a limit point of E?
It's kind of funny, but if you don't require that P be in the limit point of E, then the definition becomes kind of uncontrollable. Okay, if you think about it, I'll let you think about it, but the definition would basically become arbitrary things could happen at certain points. Okay, so yeah, you need it. Yeah. But just think. No, forget. I don't want to. Okay, so let me write this down in English, not English. Let me write this down in notation. If there exists a point with the property that for each epsilon neighborhood of Q, epsilon is greater than 0, there exists a punctured neighborhood of P such that f of the intersection of that punctured neighborhood, with E is contained in the epsilon neighborhood, right? Then we say that the limit of f of x is q as x approaches q. Let me write that again. Then we say that the limit of f of x is q as x approaches q. For those of you in the back who can't see it. Okay, I'll write that again. I'll write exactly the same thing again. Okay. Rephrased, but it's exactly the same statement. If there exists a Q and Y such that given any epsilon, there exists a delta such that if x in E satisfies that the x distance from x to P is less than delta, then the y distance of f of x from Q is less than epsilon, then we say that the limit is Q. Susan?
Does f have to be continuous for this
Nope.
division?
Nope. We all we're talking about is limit here. So we don't care. And that's why we say punctured here. That's why we say punctured. We don't care what happens at P itself. Okay, so it's fine, it's perfectly fine if at P itself, your function does something unexpected. Okay, right? All we care is that given any neighborhood around Q, there's some punctured neighborhood around P where all the outputs stay between here and here. We don't care what happens at P itself. Okay, and that's why this is limit and not continuity. Okay. It basically the only difference between limit and continuity is that we'll get rid of the word punctured. Okay, so we'll do that in 1 second. Yes, Daniel.
So if if f is surjective, then
Yes.
then this will be the same as the continuity at a point. This definition, because you'll
No.
be able to find the points at which f of that point is equal to q.
Okay, but no, no, because you might have some other point where you reach that point Q, and that would make it surjective. Okay, no, no, it's not
No,
the
it's
same.
not gonna be the same.
Okay. Okay, so what you want to think is that this is actually, you know, your old friend of limit, but just put in new garb. Okay, don't be intimidated by this. You know, all we've done here is we've taken the graph and we've written it like this. Okay, we've written the graph like this. Here it is, right? So here's this graph. Instead of thinking of it as a graph, we're thinking of it as a mapping, right? F goes from here to here, right? And what the limit means is that it's the same thing as we have here. You know, given any bounds around L, there's some punctured neighborhood around P where everybody gets mapped into that epsilon neighborhood. Mr. L.
That delta will always be a function of epsilon then.
That delta depends on the epsilon. That's
Oh,
right. Yeah.
okay.
That you know, as the epsilon changes, the delta will change.
Yeah.
Right. Yeah. Yeah. Okay. 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 So this is basically to extend the notion of limit to our more general settings. Okay. So you guys who are here visiting, you've seen the notion of limit in from the real numbers to the real numbers, right? But now we're going to go from these things x and y, metric space to metric space. Okay. When you see the word metric space, just think real numbers to real number. Yeah, just think real numbers. That's fine. Okay. So now let's do some theorems that are things that you're familiar with from high school. So if f has a limit at p, that limit is unique. Okay, that limit is unique. So here's the picture. Here's the picture of the proof. Okay, so let's just think that we're in R2. Okay, we're on the plane. Okay, so it's basically the same proof that you saw back when you were young. Okay, so you've got this point here, P, and you suppose that there's a Q that's a limit, and suppose that there's a Q prime that's also a limit, right? Okay. So what could be the trouble? Well, the trouble is that if both of these guys are limits, then we can make the values, we can say, I can make the values around P as close to Q as I want, right? But you can also say, I can make the values around P as close to Q prime as I want. That's trouble, right? Because Q and Q prime are not the same point, right? Okay, so you say, okay, what I'm going to do is I'm going to take tolerances that are so small that they don't intersect, right? And then I'll say, okay, since this is a limit, I can make all the values around here within that neighborhood. And all the values in here will be within that neighborhood. But that's impossible, right? How could they be in both of these neighborhoods which don't intersect? Then there would be no values. Then you have trouble. Okay. So that's the idea of the proof, right? If there were two limits, then you get craziness. Okay. Okay. So let's write that down. Okay. So suppose there are two limits. Suppose Q1 and Q2 are both limits, right, of f of p. Okay. well, what are we going to do? Take epsilon, anything smaller than a half of the distance between Q1 and Q2. Right? So we look at the distance between you two guys, we take half of it, and we take something smaller than that. Okay? So we take some epsilon that's smaller than half of the distance. Okay? So that the intersection is empty, right? So that the intersection of epsilon Q1 and epsilon Q2 is empty. Right? Okay. And say, okay, well, since Q1 is the limit, right, since the limit is Q1, as x approaches P, we know that there exists a delta 1 such that f of the intersection of E with the punctured delta 1 neighborhood around P is contained inside the epsilon neighborhood of Q1. Right? So we know that there's a delta 1 neighborhood. Let's say it's huge. There's some delta 1 neighborhood, and everybody in that punctured neighborhood gets mapped inside this guy. Okay? What am I going to say? There's also going to be a delta 2 neighborhood where everybody inside that neighborhood gets mapped inside of this guy. Right? Okay, so, right, so I'm just going to put i's here. I equals 1 and 2. Okay? So there's a delta 1 neighborhood, and there's a delta 2 neighborhood. There's a delta 2 neighborhood where everybody inside of that neighborhood, that punctured neighborhood, gets mapped inside of the Q2 neighborhood. This is Q1, this is Q2. Okay. So what's the trouble? What am I going to say next? Take 30 seconds and write down the end of the proof. I'm going to go walk around. So, okay. So then what do? You say, well, look, let delta 0 be the minimum of those two distances, delta 1 and delta 2. Okay, so take the smaller radius. In my picture, it's delta 2. So take the smaller radius, and then any point x in E intersect and delta 0 star of P is such that f of x must lie in both neighborhoods, right? Has to lie in this neighborhood and also has to lie in this neighborhood, right? Because anybody who lay in this delta 1 neighborhood, the output has to be here. Anybody who's in the delta 2 neighborhood, the output has to lie here. So if you lie in both neighborhoods, your output has to lie in both of these guys. But then there's nothing, right? Then you lie in the empty set, right? Right. So this thing lies in the intersection of the epsilon neighborhood. Just epsilon. The epsilon neighborhood of Q1 intersect the epsilon neighborhood of Q2, but that's empty. And
What prevents F sends every X to the empty set? Like, why can't it send X to the empty set?
this is a function, right? So it's defined on E, right? So it's not, it has some output, right? Yeah. Okay. So f of x is going to lie in the empty set, right? Right. That's to say that there's nobody in the domain. There's nobody in the domain here. Right. There's nobody in the domain here, but this should have been a limit point, right? So it has to have elements of E arbitrarily close to it. Right. Right. But P was a limit point of E, right? And so, right, so there must be X that are in E and also in that function neighborhood. Right? So there's a contradiction. This is basically saying that there's nobody in the domain there, but there has to be somebody in the domain there because we're a limit point. Maybe this answers your question to some degree, Arya.
Yeah.
Yeah. Okay, so that's the proof of why you cannot have two different limits, right? So if you have 2 points that are both limits, you end up with this craziness, right? And so there can only be one limit. Right? There can only be one limit. Okay, how's everybody doing? Are you all right? I have no sense of your feelings, so. Yeah, this is my great flaw. I've got no empathy. So, what you feel, I can't tell, but I'm just going to keep on going. Okay, so continuity. Yeah, I think it's a pretty serious flaw, right? Not that you all understand other people's feelings, but that's who I am. Okay, continuity. So again, similar situation. You got x and y metric spaces, x and y metric spaces. You got some subset of x. You've got some point. This time the point is in the set. Okay, so not in the limit, not a limit point in the set. The point actually lies in the set. Okay, so this is a significant difference. Okay, and you've got some function from x to y. Okay, you've got some function from e to y. Okay. And so the only difference, like I said earlier, the only difference between continuity and limit is that we get rid of the punctured condition, right? We get rid of the punctured condition. We say that, so again, think of your limit of 2x equals 0 as x equals to 0, right? What do you require when, well, you want to be able to say something about that point, the point 0 as well, right? That the that no matter what tolerance you're given, even at the point 0, the output lies in that neighborhood. Right? Even at the point 0, the output will lie in the epsilon neighborhood of 0. Right? So the difference is that now Now, even at P, the output has to lie in that neighborhood, in every neighborhood of Q, right? For every epsilon. For every epsilon. Okay? But that means that f of P has to be Q. That's going to force f of P to be equal to Q, right? Because f of P has to lie in every epsilon neighborhood of Q, right? Every epsilon, the only way that's going to happen is if f of P actually equals Q. Okay? Okay, so that's the difference, right? That allows us to fill in the hole here and say that it's continuous. Okay. So here's the definition. If for all neighborhoods of f of P, all neighborhoods of f of P, there exists a full neighborhood, n sub delta, such that f of the intersection of that neighborhood with E lies inside the epsilon neighborhood of f of P. Then we say that f is continuous at P. Thea.
Why can't you use Q?
Why do I use Q? Well, because I'm going to want I'm going to want I mean, it will be equal to f of P anyway, right?
Okay.
Right.
Okay, so then if you used Q, you would say, oh,
And Q turns out to be f of P.
Yeah.
Yeah. Yeah. So I could have written it, if there exists a Q such that for all neighborhoods blah blah blah, we say f is continuous at P, and then I would say P turns out to be Q turns out to be f of P. Yeah. That's fine. Okay, so here's the picture again. So you've got some point P that lies in your domain, right? You've got some point f of P, right? You've got some point f of P, and to be continuous at P means that given any epsilon neighborhood, for all epsilon neighborhood, there exists a delta neighborhood around here such that the whole thing gets mapped inside there. Okay, so there exists a delta such that the whole neighborhood, this whole neighborhood, gets mapped by f inside of that epsilon neighborhood. Okay. Some people think of epsilon as your enemy, right, and delta is your friend, right? That epsilon is something that you're trying to satisfy, and you use the delta to satisfy it. There's some negative connotation with epsilon, positive connotation with delta. I don't know. You don't have to personify. You don't have to personify these things. I don't know. Okay. Okay. So I hope you can see that the following is clear. If, in addition, P is a limit point, then f continuous at P is the same thing as saying that the limit of f of x is f of P as x approaches P.
what is the left-hand side saying? F
If-
what actually?
If in addition P is a limit point, then f continuous at P if and only if, sorry, that's continuous. continuous? Okay. Okay. Sorry. Let me give you just one funny example. What if P is an isolated point of E? What if P is an isolated point of E? Here's f of P. P is an isolated point of E. P isolated. Is f continuous at P?
It is.
Trivially, right?
Right? To be continuous means that for every epsilon neighborhood, there's a neighborhood of P such that everything in there gets mapped inside of this neighborhood. Is it continuous? Absolutely, yes. Right? Because if you're an isolated point, oh, there's nobody else in there. Right? There's nobody else from E in there. Well, that guy gets sent to inside your epsilon neighborhood. Right? Whatever epsilon neighborhood you have, there's only one point there, and it gets sent to the center of the epsilon neighborhood. Right? So if you're isolated, your function is continuous there. Okay? So being continuous at an isolated point is true. Okay. And that's why I needed to specify this, right? I needed to specify this because at an isolated point, you can't talk about limits. Right? You don't talk about limits at an isolated point, but only at limit points. Okay, let's go. Okay. Okay, so here's a theorem that you've seen before. X, Y, Z. What am I going to say?
Composition.
Composition, right? A continuous function of a continuous function of a continuous function is still going to be continuous, right? So I've got X here, I've got Y here, I've got Z here, right? And I've got functions F and G. Okay. And X, Y, and Z are metric spaces, right? And H is the composition, G with F, right? So H is the composition function, G composed with F. Okay. Right? And you've got some set here E that gets mapped to F of E, that gets mapped to G of F of E. Okay. So what am I going to write? If F is continuous at some point P in E, and G is continuous at F of P in Y, then the composed function is continuous at P. Right? Then the composition is continuous. Okay. Okay. So I'm just going to sketch the proof of this because the idea. I want you to get the idea. Okay. So here's the idea. You say, okay, here's this P here. Here's F of P. Here's G of F of P, aka H of P. Okay. Right. And what do we want to show? We want to show that if you have any tolerance around H of P, then there's some neighborhood around P that H maps into that. Okay? But we know each of the steps, right? We know each of these step things has that property, right? So we just use each of them in succession, right? So you say, okay, right? And we know that, so, right, here's the epsilon. We know that G is continuous at F of P. So we know that there's some intermediate radius here, but I'll call eta, that G maps, so that G maps this neighborhood into there, right? F is continuous at P, So I know that there's some neighborhood of P that F maps into the eta neighborhood, right? And so the composition is going to map into the epsilon neighborhood. Okay, right? That's the idea. So you just write it out. And so the sketch is like this. Take epsilon greater than 0, right? Since G is continuous, at f of P, we know that there exists an eta such that G maps the eta neighborhood of G maps the eta neighborhood of f of P 1, 2, 3, into the epsilon neighborhood of G of f of P. Right? Since f is continuous at P, we know there exists a delta such that the f of the delta neighborhood of P is contained inside of the eta neighborhood of f of P. Right? But then, right, G of f of the delta neighborhood lies inside of G of the eta neighborhood, which lies inside of the epsilon neighborhood of G of f of P. Right? Okay. So that's it. Right. I'm being a little bit sloppy because I should have intersected with E and stuff like that, but this is the idea. So I'm basically pretending that E is all of X. But that's just a detail. It's easily handled. Okay. Okay. So right, being continuous means that given some epsilon, there's a radius that satisfies it. Being continuous means that given some radius, there's a radius that satisfies it. Right? And so you compose those two machines together, and you get a machine that works from here to there. Any questions? Yeah.
You have to require that the domain of G includes the image of F.
Yes.
Okay.
Yes. So wait, let me think. Yes. Yes, that's right.
Okay.
Yeah. So, yes. Okay. But this is the idea. Other questions? Okay, let's get to one last thing. We've got 6 minutes. That should be plenty of time. Okay, so this is cool. Alternate characterization of continuity. Alternate characterization of continuity. Okay, so you've got spaces X and Y, metric spaces, and you've got some function f going from X to Y. You've got some function f going from X to Y. Turns out that f is continuous on X if and only if the pre-image of any open set is open. Okay. if and only if the pre-image of every open set is open. Yes, Susan?
So if you don't specify which point f is continuous at, does it mean that f is continuous everywhere?
Yes, I'm sorry, I should have said that. F is continuous on x means that f is continuous at every point of x. Sorry. So f is continuous at each x. Okay. Okay. So, right, so you've got these two sets, x and y. Right? And it turns out that being continuous is the same thing as saying that the pre-image of any open set here, the pre-image of any open set is also going to be open. Okay. Okay. That's kind of cool because as you see, it's got nothing to do with the metric. Right? This is a metric-free definition of continuity. If you take a course in topology, you may not have a metric, and this is actually what you use to define continuity in a more general. This is a way of defining continuity when you don't even have a metric. So let's do it. So prove. So let's suppose that f is continuous. We want to show that f inverse is always open. Okay. So let V be an open set. Let V be an open set. So we want to show that F inverse V is also open. Okay. Okay. So here's the idea. Okay, here's the picture. Watch. Watch. Okay. So okay, so we pull back to F inverse. Here's F inverse V, and here's some point here. Here's some point in F inverse V. Okay? And we want to show that this is an interior point. Right? We want to show this is an interior point because we want to show every point is interior. Right? And so what do? We map it forwards to F of P here, and we say, okay, V is open. V is open, and so I know F of P is interior. Right? F of P being interior means that there's some radius around here that lies inside of V. Then I use continuity. Right? I pull back to continuity. I say, well, by continuity, there's some delta neighborhood here that gets mapped inside of there. But that means that that whole delta neighborhood must lie in F inverse. Right? That whole. Right? So let me write it down. Pick any P in F inverse V. Right? Then since V is open, so F of P is interior, i.e. there exists an epsilon neighborhood around it that's contained inside of V. Next.
How does this define continuity without a metric? Because don't you need a metric to define openness?
No, you don't. You don't. I'll talk to you later. Okay. I mean, now we do, later you don't. Okay. Okay, so F of P is interior, so there's some epsilon neighborhood. Now we use continuity, right? By continuity, right? F is continuous at P, so there exists a delta such that F of the delta neighborhood of P lies inside of V, right? Lies inside of the epsilon neighborhood, which lies inside of V. Right? There's some little neighborhood here, so that this neighborhood lies inside of that thing, which lies inside of V. Right? But that means that this whole neighborhood lies inside of the inverse image, right? Inside the inverse image of V. right? Right? But that means that P is interior. Okay. And so you see that if F is continuous, then every pre-image of an open set is still going to be open. Okay. And then the opposite proof is also pretty similar to this. Okay, so I'll leave it. Okay. So I'll let you read the opposite proof. Okay. Okay, that's it for today.